Okay, then let's start. Yeah, thanks for coming and joining my talk about laser trimming. As this show is called Sensor and Test, I will focus on, in my talk, after a short introduction of the laser trimming technology itself, I will focus on sensors, especially on pressure and temperature sensors. But first, I want to give you a brief introduction who is talking here today. So my name is Niels Krauch. I'm 40 years old, and I'm managing director and CTO of the Photonics Systems Group. So who is Photonics Systems Group? So we are a laser manufacturing equipment manufacturer. We specialize along the value chain of electronic manufacturing. That means aside from the laser trimming, which I will showcase today, we're doing some other laser processes like drilling holes in advanced PCBs or cutting ceramic substrates, or also some stuff in the semiconductor industry. Yeah. Maybe you don't know the name Photonics Systems Group. In the past, we were called Inolas or Eltris or even Electronic Production Partners. There are multiple names around, but since 2023, we are combined under the umbrella of the name Photonics Systems Group. So laser trimming is everywhere. I mean, that's a bold statement, and you might heard something like that before in some other talks. But is laser trimming really a niche technology? I doubt it. I mean, every one of you has a smartphone in the pocket or a laptop you are working every day, and in these electronic devices there are chip resistors, for example. Every chip resistor in the world is laser trimmed. So there is basically no other technology doing that. So chip resistors, there are trillions or billions in annual production of these small devices, and mostly of them are laser trimmed. Because it's a very cost-effective and precise way to bring the chip resistor on a target. But as this show is called Sensor and Test, I will not talk about chip resistors today, so I focus more on more niche technologies for laser trimming, like temperature sensors and pressure sensors. But what's the idea of laser trimming? Maybe we start here. What we do is when we're talking about laser trimming. Laser trimming is basically changing the electrical property of a device with a laser. And the whole idea of this is that while we are doing this, so basically, unfortunately you cannot see my pointer here, but basically we have a laser source which ablates material on the substrate here. And while we are ablating material on the substrate, the electrical property is changing. In, let's say, 99% of all cases, we're changing the resistance of the values of the resistance of the resistor here. There are some niche applications where we do something else, but let's focus on that. So while we are ablating material here, we're measuring in real time, so that we are we're probing the substrate itself, and while we are ablating, we are measuring the electrical properties here in real time and feedback them directly into the laser and galvo controller to change the laser direction or the laser power or whatever is needed to bring the device under test in the target range. Yeah. Why we do that? That's the main question. Every production, when you manufacture a substrate today, you always have distributions in the process. So there is no ideal process. Even if you are in the front-end manufacturing of a semiconductor device, there are always distributions that you are away from your target range. The distribution is too wide. You are not in the target range you desire to have. So and with the trimming technology, we can bring that back into the target range. So before trimming, you are basically here in this range. So if a wide distribution, and after measuring, ablating material, you bring back the resistor here in this range. So of course, there are other ways to do it. You can basically add an additional device like a digital correction module to do that in a digital way. But either way, you have to you have to connect the device then, and you have to probe it, and you have to program it. So the laser trimming is a really cost-effective, really fast way to do it. When we look at that, so for example, for a chip resistor, you are in the 10 millisecond range to bring one chip resistor back in the target value. For a temperature sensor, we come to that later. It takes a little bit longer. We are in the 300 millisecond range, but to do that, this is a really fast and reliable process to do it. And of course, with all the miniaturization trends today, laser technology itself is a really precise tool. So you can do this in the up to the sub-micrometer range in precisioning. And of course, the process is non-contact. Aside from the probing of the device, it's a non-contact process, and it's comparable fast. Let's look at different cut shapes. Of course, you can remove the material in different ways. Here, there are tons of different cuts you can do. Cut shapes, cut geometries you can do on a device, giving you different advantages. Let's focus, for example, on an L cut, which is a pretty typical cut. It's in the market since forever. And with the first leg, you have a comparable high change in resistance, and then you trim until a certain value, and then you do the fine tuning with the other leg in the other direction, with a smaller deviation of resistance change. And of course, different cuts have different advantages. Serpentine cuts, for example, you can add a significant increase in resistance of the whole substrate in a pretty short time. A shave cut is a pretty precise way to do it. So you change the resistance value pretty slow. And of course, there are combinations of that and completely free forms. So there is basically no limitation on that. When we're looking at where laser trimming is used in the we can look at a matrix like that. So there are different base substrates and different layers you can apply to, and then you create different types of devices out of it. So, for example, when you for pressure sensors, you apply a thin film layer like nickel chromium to a ceramic substrate, or on a ceramic base substrate, you can deposit a platinum layer to create a temperature sensor, or chip resistors with thin film. You can do the same way. This is a cheaper way to do it. Is it with thick film pastes? They are not deposited; they are printed. This is used for hybrid circuits, also for chip resistors, and multiple other devices. But also in the semiconductor world, on wafers, you can apply thin film metals like aluminium, also for pressure sensors, temperature sensors, Hall sensors, MEMS devices, and multiple others. Also, in the mixed signal world, for analog digital converters, or the other way around, you can trim them with trimming systems into the target. I come to that later, a small overview, because there is a different technology, at least in our house. And also on PCBs, there are complex circuits like amplifiers or stuff like that. They are trimmed directly on the PCB. So we put in the whole PCB into the system and trim the whole device on the target level. Let's have a look on some use cases. You all have seen that probably. It's a standard PTI 100 down on the right side. So in the RTD platinum sensor world, there is the most common ones are PT100, PT1000. What does this mean? Basically, they have a resistance of 100 ohm or 1000 ohm at 0 degrees Celsius. Yes, but as I mentioned before, the manufacturing world is not perfect, so you have to trim them in the target. And you can imagine a temperature sensor. I mean, how you want to, you need to trim gain and offset here, but the challenge here is, of course, the sensor is in your machine and it already measures something. So where are you at the end? So there are different ways to do that, to compensate that. One of them is, of course, heating up the substrate to a certain temperature you already know, integrate temperature sensors inside the chuck top and integrate this in our measurement system in real time, or we have to say control the temperature around the substrate by basically do this in a climate chamber. Typically, it's a combination of all of this, because here, at least in the Western world, we're focusing on pretty precise temperature sensors. When we look at this, at the achievable epoxy on the resistance value is 0.05%. That means it's basically a temperature accuracy of 0.04 Kelvin. So that's, I would say, pretty precise. Most of us don't need that. And when you measure your temperature at home, that might be a little overkill. But of course, there are applications around where this is necessary. So what we do here, what is the trim type we are using here? What you see on the right side is a typical digital trim. So there are analog trims. What you saw in the slide before with the different trim cuts, this is all analog trims. Why analog? I mean, we're changing along, we are removing material, we're changing the resistance value more or less linear. With this digital trim, you open up a small little circuit here, and this is changing the resistance of the whole resistor in a predefined way. So, for example, that leg or this link here is changing the resistance by 5%. Then typically you do a measure and predict. So you measure the value, you predict which links you have to open, and then you open the links, measure again, and bring it into target. This is this is potentially the fastest way to trim something in target, because you can make a huge change with a pretty easy way, with one small little cut. I mean, this is 20 microns. This area here is in the range of 8 microns here. So you can imagine this is pretty fast. But to achieve this the resistance or the target values I'm claiming here, you have to do a combination. So it's typically it's a digital cut or a digital trim for the fast change, and then you do an analog cut for the fine tuning of the sensor. What kind of laser sources you can use here? Of course, in the past, this was all done with nanosecond technology, which is a cost-effective, good way to do it. But of course, technology is evolving. These days, we're using picosecond. That means this is 1,000 times shorter pulse than the nanosecond pulse. That means we bring in less heat into the material. Means we don't. And of course, when we're talking about a temperature sensor, that can matter, of course. Another way are pressure sensors. A pressure sensor is at the end, it's a pretty simple way. It's a piezoresistive Wheatstone bridge, which is applied to different on base substrates, like ceramic base substrates in the most easiest way, metallic base substrates like the one you see here, or even on wafers, what you would see here and here, but it's a little bit small. And what happens is when you apply a positive or negative pressure to one side of this bridge here, you see some distortion of the surface, which imbalances the bridge here, and you can basically measure a voltage, which gives you a direct value of the pressure applied to this device. I mean, it's used everywhere with this kind of technology. Like this is a gas pressure sensor here on the lower right side. This is a blood pressure sensor here, and this sensor here is, for example, used in gas tanks and stuff like that. So safety relevant stuff. What we do here, of course, we also correct offset span and basically the bridge imbalance. The main challenge here is you have to trim different values, different resistors on the whole Wheatstone bridge here to bring this in target. Of course, yeah, as this is a Wheatstone bridge, this is a voltage trim. You have a typical trim range in the magnitude of 0.1 millivolt per volt, that with an accuracy of 0.02%. When I say, hey, we trim this bridge here, that means, yeah, we bring it to zero. That's basically what we want to do here. Laser sources used here is typically also nanosecond, but also here the technology involves instead of ablating a thin film and then adding a photolithographic process to get these structure here on the substrate, you can also use a laser. So you can get rid of a photolithographic expensive process and do this directly with a laser. Pretty interesting technology, which also already works. So it's nothing in the future, it's already there. And for that, we're typically using femtoseconds lasers, because you need a really clean ablation to bring the bridge into the target range. Yeah, and of course, I represent a laser system manufacturer. So I want to showcase you what we are doing in this field. On the right side, you see two of our machines. Our LT50 series, which is a circuit trimmer for ceramic, PCB substrates, metallic substrates, and our wafer trimmer on the lower left side, which is used for up to 200 millimeter wafers. Yeah? It's basically from 50 millimeter to 200 millimeters. We can fully automatic process all these substrates. All the substrates contain a probing system, a high-end probing system to fastly probe single or multiple dies. All these systems are automation ready. So on the lower side, you see there is already a 200 millimeter automation applied to it. So you can run this system fully autonomous, doing night shifts or even doing the weekend. All this, and of course, these systems have the possibility to, with an open architecture, to attach third-party measurement systems, especially in the field of the wafer trimming. Complex testers are connected to these machines. But of course, and that's I think one of our core competencies is that we have our proprietary, we call it V2000 measurement system, which we developed in the last couple of years. So it's basically a nulling bridge and multi-measurement unit. We can say that today it's the fastest instrument in the market. So of course you can use an HP or Keysight to measure in a pretty precise way, but that takes time. Our system here can, in the mid-range section, it can measure more than 300 resistors per second. And when you look here at this curve, with some values from competitors or even our system we had before, you see we outperform all this stuff in all these systems by multiple magnitudes. So our trimming range is from 5 milliohm to 1 gigaohm, with highest accuracy you can achieve in the market. 20-bit ADCs, DACs, and for we can either force current or force voltage. If you force voltage, we can force up to 40 volts into any circuit, or if you force current, we can do it from 100 nanoamps to roughly 1 amp. We also have an active guard to get rid of any leakage in the circuits. Yeah, that's pretty much it. Thank you for your attention. And we are at booth 555, so if you have any more questions, just join us. Yeah? And of course, if you have a trimming application, we are in the Munich area. If you have any trimming application in your production or you want to enhance it, introduce it new, just let us know and you can stop by and make a live demo with us.